also live streaming on Facebook and on YouTube. So we're reaching out to a lot of folks tonight. There we go. Good. So I'll go ahead and get some of the pleasantries out of the way. I'm Ken Owen, and I'm Executive Director of Channel Islands Restoration. And we're so glad that you could join us tonight. Our guest is Susie Arts, and she's going to talk about of course, as the screen says there, the geology of the Central Coast. But what was really cool is that, what was it, about 10 years ago we made this movie? No, just kidding. It was last year. It was in the wintertime. It was right after like the first storm. We made a movie. We had a whole crew out there, 2 cameras going, Maury Spellman and I, and board members, and Lizzie Source, another employee for CIR, and microphones, all that great stuff, props, and that Susie was holding up. And it was really our first attempt at making an educational film that's something other than, 2 minutes long. And I think you're going to be really, really happy with it. And if you're a member, become a member of CIR, or if you are already a member, then you'll have a chance to check that out. So like the sign says, Channel Islands, the slide says, CIR, Channel Islands Restoration, is a 501c3 nonprofit organization. We do habitat restoration contracting, and we do environmental contracting and environmental education. At some point, we might as well put research on there as well, because that's a big component of our restoration contracting as well. It sort of falls under that category, but we are, as I said, I think earlier, celebrating our 20th anniversary this year. So we're really delighted that we've been around for 20 years. We started on Santa Cruz Island and have been spreading out like the roots of plants for a long time. So as the slide says, you can go to cirweb.org/webinars and see a whole bunch of different webinars that we've put on over the last couple of years that have just been fabulous. They're well attended. People really enjoy them. People learn a lot. They're all archived there. So check them out, because there's a lot of topics that you'll find interesting. The Channel Islands, natural history, some cultural history about the Chumash people and other indigenous people. Really great stuff there. So do check that out. I want to introduce Susie now. Susie Bards grew up in rural Pennsylvania, playing in the wooded hills and rocky creeks outside her house. After college and graduate school, she married and came to Santa Barbara in 1974. She enjoys hiking, backpacking, and she holds a degree in geology from City College, Santa Barbara City College. In 2009, she helped complete a project publishing the maps of the legendary geologist Tom Dibley, who was her friend and mentor, and in whose memory she dedicates all her field trips. As a geology educator, Susie has worked for over 20 years with schools and community organizations to bring an awareness of earth science to the general public in outdoor settings. She lives in Santa Barbara with her husband and assorted cats, and has 2 married daughters and 3 darling grandsons. So Susie was also on the board of Channel Islands Restoration, served as our board secretary for several years, and has tromped around the San Marcos foothills with me in the past extensively and helped educate me about the geology up there, which was really neat. So with that, I'll turn it over to Susie. And we'll come back in the end. And excuse me, before I do, we'll come back in the end and you can type your questions into the Q&A and we'll be able to answer questions. And I hope you have some for Susie because she's very knowledgeable. And as a reminder, there's a movie that goes along with this presentation, a really cool movie we put together, started last year and just finished up. And that is available as a gift to our members. So if you haven't joined Channel Islands Restoration and you're interested in watching this movie, just go to our webpage, cirweb.org, and hit the donate button. With that, I will now turn it over to Susie Bartz. Hey, Susie, go ahead.
Okay, Ken. I'm hoping that my voice is coming through to everybody. If there's any problem, Maury, maybe you can let me know, or someone. But thank you for that introduction. I would also like to say that I'm not a professional geologist. I'm not a licensed geologist. I'm a naturalist who just loves rocks. I love being outdoors and I like to go around waving my arms about the rocks. And so it just seemed natural that Arroyo Burro would be a great place to do this. Thank you, Ken, for having the vision to do this film. And Maury has helped me a great deal with his technological expertise. We were quite a crowd going along the beach, and I believe it was in January, with all of the holiday crowds walking up and down the beach and watching this thing going on, and some dogs coming and going. But we just walked along the beach, as you see in the picture right on the screen right now, with the cliff to our left and the surf and the water to our right. And we walked down the beach about a mile or so and looked at the interesting features that were presenting themselves as we went along. This beach is sort of my go-to beach because I don't live very far away at all. And so I've become very familiar with it and just realized I've been coming down there for over 40 years. But it's interesting because every time I go, something different is happening. And as Ken mentioned, we did this in the winter. A couple of days before this film was supposed to happen, there was a huge rainstorm. And I came scampering down to this beach to take a look at what was happening at the creek, where the creek empties into the ocean. And you would see that from the left-hand side of this picture on to the ocean on the right. It didn't look like this at all. There was rushing water coming down, a torrent of water coming out of the hills, and a big it was cutting a canyon in the sand, and there was no way we could have gotten across the outlet to the creek. But fortunately, when it was time to do the film, the sand had been brought back in by a high tide, and it was a lovely day, and so we lucked out. So the movie starts with me waving my arms, and this is the backdrop. We're here at the estuary of Arroyo Burro Creek, and the estuary is actually off the picture to your left, and it is a beautiful estuary just for birders, just to look at what's going on in an estuarine habitat, which has fresh water being supplied from the land, but also salt water coming in with the tide. So what happens there is an interesting mix of those two kinds of waters, so that the creatures who live there and the plants that live there are adapted to that kind of a habitat. So after looking at that, we turned our way and our eyes to the cliffs. And I should say here that Arroyo Burro is one of about 50 different watersheds that bring material down from the high mountains, which are the backdrop of our beautiful city and our coast, bring water down and out to the ocean. And they are the supply for the sand that is then picked up by a current called the Longshore Current and distributed along the coast. So the coast runs east-west here, and Arroyo Burro as a watershed is about halfway across this central coast and the east-west part of it. So it's a good place to start. The interesting thing, though, is that this place is always changing. So every time I walk it, and I've done it a lot, I notice something different. And the more familiar we get with our landscape, the more we're going to notice all the differences that are happening and what a dynamic place we live in. So one of the things I hoped in the film to highlight was the interrelationship, not just between the rocks, but between the action of the surf. How does that act on the rocks? What are the waves doing to the rocks? What is the sand all about? What are the cliffs made of? And how come the sand doesn't come from the cliffs? And, you know, a lot of people think that, but that's not the case. So when we look at the cliff, as we are here in this slide, we're looking at a mudstone or a shale, which is called the Monterey Shale or the Monterey Formation. And it has lots and lots of layers. You can probably see them if you look carefully, how they rise up on the right and then they kind of wiggle around and they go down on the left. And it, like many sedimentary rocks, it has lots of layers, but they are not flat as one would expect if you're studying it out of a book. How do sedimentary rocks form? Well, they build up in layers over time, but these are not flat. They are definitely folded up, and they are not the source of the sand. So what's going on here? We walk up close to the cliff and take a really close look at what does it look like? What's it made of? And I would encourage people to carefully go to the cliff and take a look at it, but always keep an eye to what's above you and what's around you, because the cliff is very fractured. It's very loose and pieces of it can fall, and you don't want that to fall on you. So next slide, please. Okay, so here's a little diagram that I made that shows why those layers in the cliff are not flat. They're in fact folded up into a series of, they're like wrinkles. There are arches, and we call that an anticline, where the layers are folded up. And then they go down into a syncline, which are the rock layers dipping down. But essentially, these layers are many. And so they are like an accordion. They are like a whole group of wrinkles, or the rocks in this particular formation have been squeezed together and subjected to a tremendous amount of compression. And that is the overriding tectonic regime in our area, the compression and the deformation of our rocks. As a result of that deforming and compression, the rocks have been lifted up, and most of them started out at or below or near sea level. But and the Monterey Formation is no exception. But where we see them now is 3,000 to 4,000 feet high, like the mountains behind our town. That's just one side of one wrinkle, and the coastal mesas are another wrinkle. And as we walk along La Mesa on the beach, we're walking along the side of an anticline because the rocks are dipping down toward the south, all along there. So the Monterey Formation was raised up from the ocean floor, and that's how it originally was formed, as a loose, gooey sediment. So can we have the next slide, please? Okay. So when people take a close look at what's in the Monterey under a microscope, they see a lot of hash, which is like the lower left picture in the page showing diatoms. They see a lot of pieces of little tiny critters. And the Monterey was formed from those, among other things, but it has a high percentage of these organic things. These are little sea creatures that live by the gazillions in the ocean. And when they die, their body parts kind of fall down to the ocean floor, and they form a gooey kind of oozy mud on the ocean floor. And eventually, more and more of them build up, and the goozy layers at the bottom get buried, and they get compacted and get cemented and turned to stone. Well, the other layers on top, which are younger, are still oozy and goozy, like it would squish up through your toes if you were walking on it. But that's the way the Monterey formed. And it is the source of the oil because of the high organic content in the Monterey Formation. And we'll talk about that later. But for now, let's look at the next slide. Thank you. So as we walk along the cliff, this is another area at Eagle Canyon. So the cliff is on the other side, but what I want to point out is all of these layers along the beach sand. This is called a wave cut terrace. And that's the next thing that we are aware of as we're walking, especially in the winter at Arroyo Burro, is oftentimes we see these tilted sort of edges of rocks sticking up. Some of them stick way up and some of them are deeper and they've eroded away, or they're softer. And those are the cutoff edges of the same rock layers of the cliff. But what happens is that the surf comes in and it strikes the base of the cliff. And here we have an amazing sense of the huge power of water on our planet. What it's doing here, as the surf comes in and the tide rises, it undercuts the layers of the cliff to the point where one by one those layers collapse and fall down into the surf, and they get carried out to sea, and they go back to being a very fine-grained material, like a mud or a clay. Okay, but at the surf line, the cutting ends, the waves are abrading the tops of the cutoff layers. And so that's how we basically get tide pools. The layers in the Monterey are all different. They're made of different kinds of sea creatures. Diatoms is one. Foraminifera or forams is another. The diatoms have a lot of silica, which is a hard resistant mineral in their hard body parts. And the foraminifera have calcic body parts, which are not as resistant. And so we get a variation in the hardness of the layers in the Monterey, the colors of it, how much oil does it have in it, was it formed in a deep ocean or a shallow ocean or a highly saline ocean, was it warm, was it cold, etc. So the Monterey, if we study all the way through the layers, we can get a fairly high resolution picture of climate change. And that has actually been done in the Santa Barbara Channel, where they have cored down into the base of the channel and then taken a look at all those layers that they're able to bring up. So let's go to the next slide. And I don't know if you can guess what this is, but obviously it's a fossil. We do see fossils if we're lucky when we're walking on the beach, and it helps to know where they are. This is not the first fossil that we come to walking on the beach, but it's a really good example. The first fossil we come to on the beach is in the film. And for years, I walked by the rock where it was encased in the rock, and I never saw it because it was on the cliff side and I was on the ocean side of this rock sticking up. But finally, one day I went to the other side, and oh my goodness, there was a bone encased in the rock. By golly. And I poured a little water on it to bring up the texture of the bone, and I did see that it was a fossil of some kind of large, probably of a marine mammal. What we're looking at here is a little more typical of what we see if you go further around the point at Arroyo Burro Beach. Once you round the point, let's see, once you round the point, you get into something that's almost like a boneyard. And you do see things like this. They're not quite as well exposed, but this was a beautiful picture, and I couldn't resist taking this picture. But you do see shapes like this in the rocks. And what we're looking at here, I believe, is a vertebra, a cross-section of a vertebra. And you can see the shape of it. You can also see below it the fine, fine layers of the hard Monterey mudstone. So one thing that helps to identify a fossil is that it has to be in a really hard rock. It has to be well encased in the rock. If the rock is shattered or has a lot of cracks in it, you probably won't see a fossil because water gets in there, in those cracks and in the shattered pieces, and it will weather out whatever organic material is in there. Water is a huge weathering agent. But in this case, the bone got encased in a hardened rock. How does that happen? Well, if we go back to the beginning of how the Monterey was formed, with that gooey ocean floor, there were whales and porpoises and dolphins swimming around back then in the Miocene. And when they died, they fell to the ocean floor. Other animals ate their soft parts, but their bones got buried in with the fine, fine layers of the mud. And you can see how by the point of the pencil, this bone is pushing down into those layers. The bone is sitting there at the expense of the layers in the mudstone. And that's another thing to look for. And the other thing you look for is the color, the texture. Remember that a lot of bones have marrow in them, and sometimes the texture looks kind of spongy as a result. In this case, we can see the color looking rusty because oxidation has taken place. That's another weathering process. So let's, hold on a second, I have some notes here. I don't want to get too far ahead of myself. But do be aware, if you go around the point, and it's a little less than a mile maybe. If you round the point, you need to be very, very aware of what the tide is doing. So every time you go to the beach, please be aware of the tides. Are you going on an ebbing tide? Or are you going on a flooding tide? And how high is it going to be? Or how low is it going to get? Most of the points along the central coast where the rocks stick out into the surf, you really don't want to get around those unless the tide is on its way out, and it should be less, well less than a +3. You want it down at a +1 and maybe less. A minus tide is really great, and we have some of those in the winter. So that's just something to keep in mind, because you want to be able to turn around and get back without getting wet. Okay, so I think that's what I need to say about fossils. But do go down to Arroyo Burro Beach and take a look at the bones. because they're there. And once you see one, you'll know what to look for. And it's really fun. Please take kids. They really get excited with this. So then the next place that presented itself was a place that we call the Pigeon Arch. Well, it's not an arch at all. You can see in the picture how it looks like an arc, but it's not really an anticline at all. Look at the way the layers are tilted. They're all pretty much tilted on the same plane, but what gives shape to the arch is the fact that the way the layers are weathered in an arcuate shape. And if you look sort of at the middle of this picture, you'll see a fairly large gap between those layers. And if you look really carefully, as you can on many occasions see that there are pigeons in there. It's really fun to count the pigeons. But in fact, they do get in there. They find a place where they can get a hold. They don't nest there, but I believe they roost there. And their sign is all over the sand. They drop their pigeon droppings and their feathers. So that's a sign to you right there. But look up, and on a good day, if the sun's not in your eyes, you can see a pigeon. In the movie, we actually found one that flew up in there and joined his companions. What interests me about this as a geologist is partly the pigeons, but especially that gap that the pigeons are making use of. What's that gap doing there? Why is there a gap? What formed it? Or what used to be there? So let's look at the next slide, and we'll have a talk about volcanic ash. Okay. Now this is another place where I happened to get a really good picture of weathered volcanic ash within the hardened layers of the Monterey. There's a lot of these. As you walk, if you walk on a good day all the way from Arroyo Burro to Ledbetter Beach on a good low tide, you will see a number of layers that look like this kind of rusty one, and most of them are somewhat recessed. And the reason for that is that they were formed from volcanic ash. How did that happen? Well, if we go back to the Miocene, we're looking at 23 to 5 million years ago, when the Monterey was under the ocean being laid down. All those little sea creatures were forming the ooze on the ocean floor, and the layers were building up. But the other thing that was happening in our region was volcanism. So think about the Mojave Desert. Okay, there were a lot of volcanoes that were spewing off in the Miocene, as well as much more recently. Think about Morro Bay. And those were somewhere around the 21 million years ago or so. The Moros are a whole line of volcanoes. Our local volcano, the closest that we can get to, is Trankion Mountain. That's, I think, erupted about 24 million years ago. And all of these different volcanoes spewed ash up into the atmosphere, which then very slowly filtered down onto the ocean and found its way down to the ocean floor. And for a big eruption, it was enough to build up a layer of volcanic ash. The reason it's so recessed is that volcanic ash is much more easily weathered. It's a softer thing than those hard layers of diatomaceous Monterey shale. And so where there is volcanic ash, it weathers away, and you see a gap in the layers in the surrounding or adjacent layers. And in the case of the pigeons, there was a big gap because there was a lot of ash in there, and you can actually go up and pick away at it. And it's kind of yucky. It's sort of rusty colored, and it's loose, and Yeah, it's easy enough to recognize once you know what you're looking for. So thanks to the volcanic ash, the pigeons have a lovely roosting place. Um, Another example of erosion and weathering. So let's go to the next slide. And we're going to talk about the oil now. So here's a very, very simplified diagram, cross section of seafloor mud, typical of the Monterey. And you see an anticline in the center, the arch-shaped fold in the rock layers with a syncline on either side. So what's happening here is as these rock layers are folding, the synclines formed a deep ocean basin. And it turns out that at that time, at that depth, there was not a lot of oxygen way down there. It was what we would call an anoxic basin. And so the body parts that were lying down there kind of, they became like an underwater swamp. So it turns out that the soft body parts of those diatoms and foraminifera, forams, those soft body parts contained lipids, and a lipid is a kind of an oily substance. The hard body parts became more brittle layers, and I've tried to show the brittle layers as those kind of little V-shaped lines. There is a brittle layer in the middle of two more coherent or more plastic layers. But the oil is forming at the base of the syncline on the right, and the red arrow points to how the oil and the gas that form down there, how they move up through the seafloor and find their way to the top of an anticline. Now, this is very simplified, and it's not the whole story. But think about this, oil is not so dense. It floats on water, right? So it wants to get up out of those basins, and where it finds a shattered layer of brittle rock, it finds little places where it can find its way through in the cracks, and it finds its way up until it gets to the top of an anticline where there happens to be a more plastic layer over the top of it, and that is called a cap rock. And that's where the reservoir of oil forms, and it finds its way somewhere through a crack and finds its way up to the top of the ocean, which is up to the top and off of this picture. So I think that's, let's see what else I want to say about this. Is very simplified. What really happens is quite a bit more complex. So the next slide shows a little bit more complexity. So you can see, this is another cross section of the way the Monterey Formation behaves underwater. We see it in the cliffs, but the anticlines and synclines don't stop right there. They keep going on underwater all the way down to the Santa Barbara Basin, which is offshore. But you can see from this that it's quite a bit more complicated. You do see sort of some anticlines and synclines there, but they're offset by fractures. And that has, the fractures are also the vehicles for oil migration. So the oil, you can see a little reservoir of oil there on the anticline on the left, but that oil is looking for a fracture, and the fractures are, as I said, a major vehicle for the oil to find its way up to the surface. Okay, let's go to the next slide. Okay, so now as we get further around the point, we're still walking along and we come upon a place that looks like this in the cliff. And there are a whole series of these kinds of features. If you look carefully at it, you can see a kind of a rusty colored layer coming in from the left, and it hits a crack, kind of a diagonal crack. And then you see that rusty layer repeated on the right, but it's a little lower. It's collapsed a little bit. And in fact, you can see how the one on the left gets dragged down and then continues to the layer on the right. And that happens not only at the top rusty layer, but there's another one below it, happens again. And below that, there's a dark brownish layer with some white blobs in it. And that one has gotten severely dragged down. So the name for this is a drag fold. I just sort of like that name. But we also see in this, it's hard to tell, in the lower layer, the low kind of the brownish gray one, there is some kind of small horizontal white lines. And I believe those are what we call CFAs, carbonate fluoroapatite. The easy way to think about that is fossilized fish poop, but it's not. But it is an evidence of marine origin. It's from the detritus of dying or pieces of fish that undergo a sort of a chemical alteration called phosphatization. So that was kind of exciting to see. These have been extensively studied up at Naples, up the coastalways, by a number of geologists at UCSB. And they published a book on the Monterey, all the forams and the diatoms and all the volcanic ash layers and those CFAs, which I found very interesting, very useful. So, okay, we have this extensional fault. Now, I've been talking all along about compression, right? But here we have something else has happened. This is extension. This is like if you had a whole bunch of dominoes together and you knocked them over because you pulled apart their base, they would fall over like this, right? And that's what we have here. You can count them as you walk along the beach, and it's difficult to try and figure out why are we seeing extension that's pulling apart or collapse when I've been talking all along about the huge tectonic compression that is acting on our crust and on our landscape. And the answer is that we went around the point, and now instead of walking along the side of the anticline, we have walked around a point and we're looking down the axis of it. So let's look at the next slide. This is going to, yeah. This slide is from a field guide published by Dr. Rick Behl, B-E-H-L, by the way, who has a wonderful field trip coming up the Central Coast, stopping at Carpinteria and the tar pits, and then on up to Arroyo Burro, and finally up to, Gaviota State Beach. Wonderful field trip. And in this book, there is this amazing diagram. So I'll try and unpack it for you. What we're looking at is an elongated arch. You can tell the arch, you can see that, and the red arrows are the compression force acting that's pushing this arch up. Okay, that was probably easy enough to figure. But think about this. When you squeeze that arch up, what happens to the matter of the rocks inside? They get pushed up, but they also get kind of squeezed and squished, and the only place for them to go is getting squeezed out along the axis, and that's what the yellow arrow is trying to demonstrate. Another way to think about this is if you have a roll of clay, really soft clay between your hands, and you make it a big fat roll, okay? Big fat roll of clay. What's going to happen if you squeeze it? Okay, you squeeze it together like that, it's going to get smaller between your hands, right? But it's also going to come squishing out the sides. That's the extension that the rocks undergo. Enough, maybe not a lot, but enough to make those lovely little extensional faults. And there's, you just walk along on the beach and you see one after another as you are crossing the axis of that anticline. It's lots of fun. Okay. Well, we're getting toward the end of my discussion here, but let's look at the next slide. Okay. We have a couple of slides here that are pictures of the kinds of creatures that live at the surf zone. And we have the Monterey Formation to thank for that. It's because of those varying layers of hard and soft and hard and soft, high and low and high and low on a marine terrace that we have tide pools at all. So it's really by permission of geology that we enjoy the tide pools that we do. And these are some of the creatures that we see attached to the rocks in the tide pool area. And if you go around the point and you take your eyes off of those lovely little extensional faults and you don't look for the fossils, but if the sea floor and the wave cut terrace is bare, you will see some of these. I get excited about the giant limpet. That's the actual, well, that's really hard to tell its size, but some of them are really big like that. And they're solitary. Other limpets, like the ones on the left, are colonial. And they have an interesting life. Those are, they're live creatures inside. I've read that in some countries, in the old days, these were used in some manner as a source of baby milk. Let's look at the next slide. Okay. These are also interesting creatures, and we saw some little acorn barnacles in the previous slide. These guys in the center, these gooseneck barnacles, you can actually wiggle them gently, please. But they appear more or less on the surf side often of a rock. They seem to be able to handle the coming and going of the surf and the waves. Most of these creatures are underwater at high tide, including the chiton, the one on the left. They sort of remind me of the center of a trilobite, but trilobites were long gone millions of years ago. So, but these are actually alive. They have a very strong glue. They have eight segments that actually move, and they do move around when the water comes in. The picture on the right shows you a colony of sandcastle worms. And I think there's one more slide. Let's take a look at that. This is what a sandcastle worm looks like real close up. Those are the little white balls, or I think the pieces of sand. When the tide comes in, the worm comes out and uses a siphon to get its food. But isn't that beautiful? It's just amazing. Those you see in the protected parts of the rock, underneath overhanging rocks and on the side away from the surf to protect themselves from the power of the waves. So basically, the sea life is really part of the picture here, along with the sand, along with the surf, the air, the waves. We have an incredible richness in the Santa Barbara Channel and the land that is formed around it. At this point, I'd like to end by giving some credit to people who have helped me. Do we have another slide? Okay, this was Tom Dibley, who died in 2004, but whom I knew and whose maps I helped publish. This photograph was taken just 6 months before he died, and we owe him a great deal. He was a legendary geologist and left a great legacy of beautiful geologic maps. I'm also thankful to Tanya Atwater, who has been a great resource and inspiration in her work all through the years, especially to Santa Barbara City College and many other people for their support over the years. I didn't do this by myself. I don't do field trips on my own by myself. I have great help. And I'd like to end by calling attention to Ed Keller. I'm incredibly grateful to this man. He died on the 9th of September, and I was never his student, but we shared, Ed and I, and many others, a great interest in landscape and the geologic processes that are at work in it. With my questions that I peppered him with from time to time on emails, he was very approachable. He responded to them. He was very generous in the way he shared his resources, scientific papers and maps, images, diagrams. Ed had a huge interest in our landscape. He dated our marine terraces, and I found that in itself very interesting. But he also did a lot of work after the Montecito debris flow and in helping our community to understand how that happened, why it happened, how long ago it happened before, and the chance that it might happen again. So he will be greatly missed by our whole community, where he gave so much of his expertise in public service. And with that tribute, I am finished with my comments, and I would entertain any questions. Thank you. I'm going to turn this over to either Ken or Maury, if there have been any questions. No? Okay.
Yes, thank you, Susie, for the wonderful presentation. If anyone has any questions, they can submit it in the Q&A at the bottom of your screen.
Okay.
Well, Dennis Houghton says, thank you so much, Susie.
Thank you, Dennis, for coming along. I should say that Dennis was my cue card holder, and during the making of the movie, he was very helpful. Okay.
And Paige wants to know, can you give an age range for the Monterey Shale in that area?
Yes.
And she also thanks you for the wonderful presentation.
Thank you, Paige. Thank you for coming. And yes, the Monterey Shale at the Arroyo Burro Beach is somewhere between 12 and 15 million years old, which means that it was laid down as a sediment on the ocean floor that long ago. The process of making it into a rock took some time, and then by 5 million years ago or so, after all of the compression, it finally rose out of the water and formed the cliffs that we see today.
Okay, getting some more thank yous from Ray and John. John wants to know, do you get sneaker waves on the Central Coast? Do you know what those are?
I have no idea what a sneaker wave is.
Okay.
There's always something to learn. Yeah. Okay. I'll have to look into that one.
Let's see here. I have a question that says, are coastal mesas impacted at all by metamorphic processes, or do the folds form because of the uplifting?
Can you read that again?
Sure. Are the coastal mesa impacted at all by metamorphic processes, or do the folds form because of uplifting?
So the folds are formed because of compression, like when you squeeze an accordion together. That's the simplest way that I can think of it. Metamorphic processes, I would say probably not, but there are processes that alter the rocks, which is not the same thing as metamorphism. But the rocks can be altered by how deeply they're buried, how much clay they have, temperature, pressure, and sometimes they can alter to a slightly different rock. So when we see, for example, the chert in the Monterey, that has been altered by those sorts of processes. But I don't know that there are metamorphic rocks in the Monterey Formation. I'm
Right.
seeing some of these. Okay, go ahead.
Yeah, Malcolm and Sarah both say thank you for the presentation. Someone has their hand up. Let me see if I can allow them to talk. Their hand's still up. Alan. Okay.
Alan has a question. Are you seeing the one about Trankion Mountain, the volcanics?
Alan, your
Yeah.
audio is on if you have a question.
Yes, I'm curious if you mentioned the Trankion volcanics and that they're about 25 million years old, which, if I recall, is about the age when the San Andreas Fault started. So I'm just wondering if there's a
How did that
connection.
Yeah, probably closer to 24 million years on Trankion, but there is a connection in the sense that those volcanics exist up the coast from our east-west area. But if you look at what's happening there, there are blocks of crust that are getting stretched as the San Andreas transform motion moves along. So the San Andreas fault itself is inland from there, but there are other faults, which we call en echelon, or the parallel to it, the Hosgri, the Nacimiento fault, other faults that are major faults that are moving in the same way as the San Andreas. And as a result of that, there are these blocks of stretched crust. And I think in some of that stretching, it opens gaps in the crust for magma to come out and form a volcano. And it's not a very good explanation of it. I have a great picture of what goes on, but I would have to leave the screen here and go get it. So, but yes, there is a relationship, and it's probably as much affected by those parallel major faults as the San Andreas that we think of when we say that, the name. Okay.
All right. A couple of people want to know if you're doing any more field trips, and I'll just jump in here and say that if you become a member of Channel Islands Restoration, you will get the complete video that we produced with Susie on the Arroyo Beach Geology Walk. So that is available. It's about 45 minutes long. But Susie, how can people contact you about field trips or about the walk?
Well, I'm sort of backing off from going and leading field trips all the time, but I do lead field trips for an organization called Nature Track. It's a foundation that takes children into the field to do their science outdoors. But I also lead field trips for community organizations on the lay level. This is not for academicians or professors. This is for folks like me and my neighbors, my kids. And some of the organizations that have sponsored my trips are the Botanic Garden, the Santa Ynez Valley Natural History Society, the Land Trek program for the Land Trust for Santa Barbara County. I am happy to lead field trips for Channel Islands Restoration as well. So those are all organizations that you could contact. And if they would like to set up a field trip with me, I'd be happy to discuss it. Thank you.
Great, thank you, Susie. And Sarah wants to know if the, is it fair to say if the darker brown and red brown thin layers within the Monterey are all volcanic ash? Or are there multiple contributors to the darker and very thin layers that she's discovered when walking along the beach?
Well, Sarah, it sounds like you are making very close observations. I would say that the rusty layers, the light brown layers, are that color not because they have volcanic ash. Oxidation is the process, the weathering process that can cause that color in many kinds of situations. And so I would say that those are layers of Monterey shale, the rock, the mudstone, that have become rusty looking because of oxidation. If you are seeing lots of little bitty layers within the more cohesive layers, we just stopped our recording. Okay. If you have seen those, you need to go up and pick at them with a hammer and see how soft they are. But be careful if you do things like that. Keep an eye up high and have a friend looking at the cliff when you're doing that. And if they start doing this, you've got to run away from the cliff. Please be very careful. Okay, here's something about sneaker waves. Sudden and unusual higher amplitude that can swamp the beach visitors and occasionally lead to drowning. Yeah, I would watch out for those. It sounds like wave construction, something that I would have heard of. Wave construction where there's some kind of a barrier to the waves that they hit, and then they get deflected outward and then come back in. And when they come back in, they're higher. Yeah, I guess I never heard the term sneaker wave, but it sounds like something that is very much to be watched out for. I don't know how you would have any prior notice if that was going to happen. Yeah.
All right. Someone asked about seeing a map of Arroyo Burrow, and Ken is going to share his screen here.
Oh, good.
And
Okay.
show us where
Thank you, Ken.
the presentation took place that we just
Can I have a mouse here? Can you see an arrow? Oh, there you got an arrow. Okay. So, this is interesting. I think I can see the San Antonio alluvial fan here. Okay, you're going to see the east-west part of the coast. You see a bunch of little black dots there. Move your cursor to the left, right there, that little black dot, that's near Arroyo Burrow, I think. Yeah. Okay, you can, yeah, you can see Santa Barbara town, actually. Okay, let me see if, no, that's the airport, so I was wrong. Okay, so Arroyo Burrow, you can stop there. And you can see the harbor, the marina, and Arroyo Burrow is right there. Yeah, I think you're, no, that's Las Positas. Isn't that Elings Park? And Arroyo Burrow is off to the right. Ta-da-da-da, a little more. Okay. I think you want to be a little bit more to the right. I'm not sure. Yeah. Okay. You're going to see a bunch of white built roofs way at the right. I think that might be part of the Cliff Drive area. There you go. And you can see Shoreline Park coming around. So Arroyo Burro, whoops, we went too far. But it's along there. It's a little bit to the left of what, let me see. I can't get my chat out of the way. Yeah, okay. I think it's off to the left a little bit where the surf is. You can see a lot of surf there. I'm not sure. You know what I thought was Ealing's Park? That's the Douglas Preserve, isn't it? Right? So Arroyo Burro is coming right through there. Yeah. I think that's the Douglas Preserve. What about the rest of you? I'm pretty sure that's right. Not totally sure. What's that roundabout? That's the roundabout down at the bottom of Cliff Drive where Las Positas takes up. Yep. Okay. So there's a map. I hope that helps. Okay. Thank you, Ken. Good.
All right, let's see if we have any more questions here.
Oh. Oops.
I don't know if you saw, but John wanted to know if you've seen oil in Carpenter.
Yes, I did see that question, and yes, there is. If you know where to look, there's a lot of oil seeping out of those cliffs at from the Carpinteria Bluffs. There's a way to get down, kind of a diagonal path that goes down to the beach, a little bit down the coast from where you look at the seals. And if you get down to the beach there on a safe day when the tide is low, you can definitely see oil coming out of the cliff. Sometimes you're walking along the beach and you see a little blob of it stick up, like a little teeny tiny oil volcano coming up out of the sand. It's pretty funny.
All right, okay, and Susan has had her hand up for a while. Let me see if I can. Oh, I actually don't think I have access to that. Do we have any more questions? Let's see.
Well, we have some discussion about the sneaker wave here and how that happens. From Sarah Killen, thank you. So I don't know if other people can see her comment, but it's interesting because she and I had the same instructor, Dr. Gray from City College. Waves that are in phase mean a wave on the return from the shore coming in contact with one coming toward the shore, and it results in an amplified wave height. That may be what a sneaker wave is. Thank you for that offering. Yeah.
Okay, well, I don't think we have any more questions. So thank you everyone for joining us tonight. If you'd like to support Channel Islands Restoration during this holiday giving season and get access to Susie's complete geology film, again, it's 45 minutes long, lots of great information. You can become a member on our website at crweb.org. And thank you, Susie, and everyone for joining us, and we'll see you soon. Susie, do you have any closing comments you'd like to add?
No, I'd just like to thank everybody for their interest and underscore what Maury has said about taking a look at the film. But I also would like to say, get out there, notice stuff, and be thankful for our beautiful landscape. We are very, very lucky to live here, and it's not just the rocks, it's how the whole landscape works together. It's good for your soul. It's a healing thing. So I would encourage you to use some time during the holidays to do that. Thank you, and have a good holiday, all of you.
Great, thank you. Have a good night, everybody.
Good night.